we can, as an alternative to analyzing the motion on each of these objects and solving simultaneous equations for the tension, and I think I didn't mention at the end of the last video that we had a couple of equations here and here, and tension was involved in those equations. We had two equations with unknowns, and by setting the two forces equal and opposite, by setting the two accelerations equal, we again get equations that we can solve for the tension. Now, and that's how we would analyze it if we consider these masses to be two separate systems. In this analysis, well, we're going to analyze this by considering the two masses and the cord or string connecting them to be a single system, and we're going to choose a positive direction as the counterclockwise direction, meaning that if the system is moving this way, it's tending to sort of rotate in the counterclockwise direction. If it's moving this way, that would be the clockwise direction. We chose the counterclockwise as the positive direction. That's a traditional choice, and then you'll see fairly soon why that's the choice that we make. Okay, so in this case, the mg sine beta that you get for the parallel component of the weight of this object and the m1g sine alpha that we get for the parallel component of the weight of this object both act on the system because, well, that should be obvious. Okay, if this is the positive direction, then this force will be positive, the m2g sine beta, and this force will be negative, the m1g sine alpha. The frictional forces will be in the direction opposite motion. And I don't know what was going on in my mind, but I wrote these as negative, and we got to correct that. These frictional forces will be positive because the motion is in the negative direction, the frictional force is in the direction opposite motion. I've indicated those frictional forces by arrows that go in the right direction. Don't know why I didn't get the right sign there, except that something might have distracted me, or I just might have not been thinking. So you got to be careful about that. That wasn't an intentional error, meant to illustrate how it's so easy to mess this up. And I think we'll also say that this is going to be mu1 here and mu2. Sorry, this is mu1. This is mu2. So we're going to have a mu2 and a mu1. Now, if the system is in motion, then that'll be mu2k and mu1k. So we're going to assume the system is in motion. And in the negative direction. So if there's motion in the negative direction, then we can also put the k here, mu2k, mu1k, meaning coefficient of kinetic friction. The acceleration is then going to be F net over m1 plus m2, and we can easily calculate that. Now you notice that depending on these coefficients of friction and the relative magnitudes of m2 sine beta and m1 sine alpha, this F net could be positive or negative. If m1 is great enough, then this negative m1 sine alpha could be greater than all these other terms. And that would, of course, correspond to this incline being steeper, some combination of this incline being steep and larger mass M1 larger than M2. If that's not the case, if this negative here is less in magnitude than these positives, then the net force will be in the positive direction and the system will be slowing down. And then it becomes an interesting question. If the system comes to rest, does it then stay at rest? Because as soon as it comes to rest, the kinetic friction is replaced by static friction. And the question is then, is all that static friction sufficient to prevent the system from beginning to move in the opposite direction? You'll notice that in this analysis, the tension force does not appear. It's internal to the system. And in many ways, this analysis is simpler. Although if we want to do an analysis of that internal force, we do need to go back to the free body diagrams for the two masses and analyze as in the preceding discussion, in the preceding video.